Hey, good morning, everyone. Okay, we'll get started on the review, final review. Do you have any question before we get started?
We have until 11:59 tomorrow night, right?
No, it's Wednesday night, right? Yeah,
For
May 12.
homeworks and
Everything is due
quizzes.
by May 12, right? So, you mean the final exam, is that?
No, I mean the homeworks and quizzes.
It's due on May 12th. Okay.
Okay, I think on Excel it says the 11th.
Maybe, yeah. So, whatever it says in Excel, but I believe I extended till the last day, May 12th. But I'll double check though. Okay. If you could finish by tomorrow, that'd be good. But Wednesday will be last day. Okay. All right. I guess we can get started on the review first, and I'll talk about the grading policies, everything after the review. So first one, let's look at the question number 1. So this is final exam review question number 1. What requires the necessary for normal probability distribution to be a standard normal probability distribution? So for the standard normal probability distribution, mu equal to 0, standard deviation equal to 1. So you got to be C, right? The mean and standard deviation, mean 0, standard deviation equal to 1. Okay, that's question 1. Question 2. So a stats professor plans classes so carefully that length of the class is uniformly distributed between 50 and 60 minutes. Find the probability of given class period runs greater than 51.75 minutes. Okay, so let me put into the note and I show you the detailed solution. Okay. All right, here you go. All right, so you're gonna draw a uniform distribution is rectangle shape, right? So we get a rectangular here, and the base is from 15 minutes to 60 minutes. And then we know the total area, total probability, total area here is equal to 1. If the base is 10, right? 50, between 50 and 60, the base is 10, then the height must be 1 over 10. And then the height is what we call the probability. P of x equal to 1 over 10.1. Now, they want to find out the probability given class runs greater than 51.75. 51.75 is right here. Greater than that, they want this area right here. So you're going to use the base times height, right? Height is 0.1. We just figured out. So the probability here for class greater than 51.75 will be the base 10. No, base not 10 anymore. Okay, the height is 0.1. So it's going to be 60 minus 51.75. That's a base times the height 0.1. Okay, then that's going to be 7.25. No, 8.25 times 0.1. So it's 0.825. So that means it's 82.5%. They want to run 3 decimals, so it's 0.825. That's correct answer. Okay, so that's question number 2. And let's look at question 3. So it's 0.825. 0.825. Okay, then next, very similar one, right? That's professor, uniformly distributed between 47 and 57 minutes. Find the probability of a given class runs between these two time. Okay, print screen. Let's go to the note. One more time, it's very similar procedure. The base is also 10 here. Okay, so you draw a rectangle, and this is 47 endpoints, 47 and 57 minutes. So the base is all still 10. So the height must be 1 over 10, right? Or 0.1. They want to find between 51.5 and 51.75. Okay, so they want area between. Still we're using base times height, right? So probability for class period run between 51.5 and 51.75. Base is 51.75 minus 51.5 times the height is 0.1. So this is 0.25 times 0.1. So this is 0.025. Okay. So very, very similar to the previous one. 0.025. They want 3 decimal places. We'll keep as is. Okay. So this is question 3. Any questions so far? Very similar to your also your homework examples. Find the area of the shaded region. The graph depicts a standard normal distribution. So you are given z-score and you want the area to the left. Okay. So one more time, all you have to do is I'm gonna open the formula sheet. Okay. Well, you can also use the sheet embedded in the system. That's also fine, but I get used to the formula sheet we are using. So I'm going to use that formula sheet. So let me open it really quickly. So you go to table A2, second page of table A2, look for the area corresponds with a z-score of 0.75. Okay, let's see, formula sheet. Formula sheet. Here we go. So let's go down to the page A2. Okay, here we go. And we need to go to the second page of the table A2. And we look for 0.74. 0.74. Okay. So the answer is 0.7704. So it's 0.7704. Okay, so they want area to the left, and the table gives us exactly the area to the left. So that will do it. Now find the indicated z-score. The graph depicts a standard normal distribution with a mean 0, standard deviation 1. So standard normal curve. And they want a corresponding z-score. They give us the area to the left. So we're still using table A2, but we're going backwards to table A2. So here we go. So let's go to the table A2. So it's 0.9875. So you go into the center area of table A2, look for the closest value of 0.9875. And we do have exact match. It's 2.24. That matches with 0.9875. So the corresponding z-score is 2.2 on the side. When you look up, is 0.04. Combine those two numbers, you get 2.24. So the corresponding z-score is 2.24, according to the table. Okay. All right, so it's going backwards. You're given the area, you try to find out the corresponding z-score. Okay. And now look at the third question here. Assume the readings on thermometer normally distributed. So this is standard normal distribution because mean 0, standard deviation equal to 1, and you will find the probability. A randomly selected thermometer reads greater than 1.51. Greater than meaning we want area to the right. 1.51 is the positive number. So 0 is right in the middle. Positive number is on the right hand side of the 0 or the center. Okay, so must be C, right? And once we find out that this is correct graph, now we're going to go to the table A2, look for the area to the left first. So go to 1 point, find out what's the left area of 1.51. So 1.51 turned out to be 0.9345. So that's area to the left. but we want area to the right. So using 1 minus 0.9345. So the answer for this is 1 minus 0.9345. And this turned out to be 0.0655. Okay, so the answer will be 0.0655. Okay. All right. All right, next question 6. And question 7. Assuming that thermometer readings are normally distributed, mean 0, standard deviation 1, and a case between 0.5 and 2.25, again, they both positive. So it's on the right-hand side of the center. And one of them is 0.5, one of them is 2.25 between. So the area in between will be 8. Okay. And now, in order to find out the probability associated with this, we need to find out the area corresponds with the bigger z-score first. Let me just transfer this into the note. Come show you the detail. Area in between. So right here, we look up 2.25 first for the bigger area, right? So bigger area including the shaded region and also this triangle area. Okay, so probability for z-score greater than 0.5 and less than 2.25. So look up the bigger probability first. So we go to the table A2. And 2.25 first, 2.2 right here, and then 5. So that turned out to be 0.9878. Okay, so that's a bigger area. So let's mark that number first, 0.9878. Get that first. Okay. And then subtract smaller area, right? Smaller area is area corresponding to z-score 0.50. And that's exactly triangle area. So when you find the difference, it becomes the designated area we're looking for. Okay, one more time. Go to table A2, look for 0.50, 0.50, 0.6915. Okay, 0.6915. 0.6915, and then difference is the final answer. So this should be 3, 6, 9, 2. 0.2963. But let me just double check. I don't want to give you the wrong answer. And yeah, that's right. Okay, so I have the right answer. Here we go. 2963. Let's go back to that point. 2963. That's what we're looking for. Okay. Yeah, so that's what it is. Okay, for question 7. And now let's look at question 8. Find the area of the shaded region. The graph to the right depicts IQ score of adults, and those scores are normally distributed with mean 100, standard deviation 15. Oh, by the way, you'll find only cover chapters 6, 7, 8, and 10, right? Only 4 chapters, not the entire semester. One of your classmates emailed me about this. I just want to mention that to you. So whatever appear on the final review, right, will be similar to your actual final. Okay, so let's look at this. One more time. Zoom in a little bit. Okay, so here we go. So we know the mean, which is mu equal to 100. Standard deviation is 15. And you want to find out area to the left. IQ score here is 90, so x equal 90. So let's find z-score first. X minus mu over sigma. Okay, so 100, no, 90. minus 100 divided by 15. So it's negative 10 over 15, negative 2/3. And that's approximately negative 0.67. Then we always run it 2 decimal place. So now we're going to use that number. So this becomes a normal curve, or standard normal curve with a z-score here. Z-score corresponds with 90 will be negative 0.67, and we want area to the left. Go to table A2, and let's look for the corresponding area for negative 0.67. So negative numbers on the first page, negative 0.67. Here you go. So negative 0.6 right here. And we find the other number, second decimal, 0.07. So the answer turned out to be 0.2514. Okay. 0.2514. Okay. 0.2514. Probability for IQ score less than 90, which is 0.2514. So you put in 0.2514 for that. 2514. Yeah. Okay, that's question 8. Question 9. Very similar question, but it's an area in between, right? Just like the other one we did. We need to find out bigger z-score for the bigger IQ score, and find the smaller z-score corresponding with the smaller IQ score, and look up the probability accordingly, then find the difference. Okay. Just like the other question. Okay, one more time, let me make it bigger. So, yes, no, this is not a question we are looking for. Let me just go back. I didn't copy the question properly. Okay. Go back one more time. Okay, I'm going to make it larger graph. Okay, so here you go. So we're looking for the bigger z-score first for IQ score, right? For x equal to 120. So z-score equal to, here the mean is 100. Standard deviation is 15. Okay, so z-score for bigger IQ score is x minus mu over sigma, same formula. So it's 120 minus 100 divided by 15. So this is 20 over 15. That's 4 over 3. So that's approximately 1.33. Okay, so that's for bigger IQ score. For smaller IQ score, for 85, let's find the z-score first. Z-score equal to x minus mu over sigma. So it's 85 minus 100 divided by 15. So this is negative 15 over 15. So this is negative 1.00. So now this curve becomes standard normal curve. Now we have both z-score, right? So it's negative 1.00 and 1.33. We found out z-score, so we could convert to the standard normal curve. So the probability of IQ score greater than 90, less than 100, 85, not 90. So probability for IQ score greater than 85, less than 120. It's the same thing as saying z-score greater than negative 1.00, less than 1.33. So now we're looking for the bigger area using the bigger z-score. So let's go to table A2. Look for 1.33 first. So go to the second page of table A2, 1.33. It's 0.9082. So that's a bigger z-score, 0.9082. Let's mark that. 0.90. And let's look for the smaller area corresponds with the z-score of -1.00. Again, go to the first page of table A2, -1.00 right here. It's 0.1587. Okay. Mark the number 0.1587. And the difference is the answer. Okay. So 0.9082 minus 0.1587. And that turned out to be 0.7495. So the final answer is 0.7495. Okay. That's what you put into the answer option here, 0.707495. Okay, so this is question 9, question 10. So assuming that women's height are normally distributed with a mean mu equal to 63.4, standard deviation given in sigma equal 2.3, one woman and 43 women, right? So one woman, if there's only one woman, so that we're still using the regular z-score formula. And once there's a sample assembling here, meaning they conduct a survey, come up with a sample, then we are using central limit theorem. So that's a major difference between a regular normal distribution and central limit theorem. And we are using the central limit theorem for part B. Okay, and let's look at part A first. Okay. So now, again, you're gonna probably draw the bell curve, try to visualize everything here for part A. So here we go. And we're gonna draw the bell curve. Okay, let's see what's going on here. So the mean is 63.4. Okay, it's right here. And now we're corresponding, the height is 64 inches, is slightly bigger than that. So x equals 64. And they want less than, and the height is less than 64 inches. That tells us they want area to the left. Now, again, we're going to use z-score formula, find out the corresponding z-score. So it means that standard deviation is 2.3. So it's x minus mu over sigma. So it's going to be 64 minus 63.4 divided by 2.3. So this turned out to be 0.6 over 2.3. And that's approximately, so we run it to 2 decimal place. And that turned out to be 0.26. Okay, so the z-score is 0.26. So now we want area to left, right? So whatever you see from the table, that will be the answer. Okay. Table A2. So let's go to table A2 first. So for 0.26 on the second page, 0.2 and 6. And this turned out to be 0.6026. And this gives us the area to the left, and that's what we're looking for. We get a result, 0.26026. So the first part is 0.6026. Okay. Okay, so now we move on to second part, part B. So now we have a sample. They want to compare the sample mean for 43 women, mean height, right? So mean sample mean to the population mean. So using the central limit theorem, it's still very similar settings. The only thing is the formula changes because we're talking about different things. Okay, now mean is still the same. Notice that the z-score will be a lot bigger here. So now x sample mean equals to 64. So we want this area right here, area to the left still. But since we have sample here, sample is 43 women, and mean is 63.4, sigma is 2.3, and x bar, sample mean is 64. So we find the z-score first, x bar minus subtracting the sample mean from the population mean, dividing by sigma over square root of sample size. So this is exactly what we call a central limit theorem. Central limit theorem is used to compare the sample mean to the population mean and find out the corresponding area. So 64 minus 63.4 divided by sigma is 2.3 over square root of 43. I'm going to show you this in Excel because a lot of students tend to make mistake from my past experience, in terms of inputting this, sometimes end up with the wrong answers. So let me show it in Excel so you won't make that mistake. Okay, so I'm gonna share the screen with you in a second. Here we go. So we're supposed to put a numerator in parentheses, so 64 minus 63.4. Well, that take a numerator and then now divide by denominator. You probably want to put denominator in parentheses as well. So 2.3 divided by square root of 43. Okay, so this is a proper input, right? If you forget to put a parenthesis for the denominator, then your answer will be totally off. Okay, so make sure you get this. Now, once you put in the proper form, here you go. So 2 decimal, we want 1.71, right? So now if you compare that, the z-score actually has become so much bigger compared to the previous, right? The previous is just 0.26. Now with the same sample mean, when you compare the sample mean to population mean, when there's a sample involved, then the z-score usually will bump up by a lot. So we're looking at 1.71 in terms of z-score. So if you really want to turn into a standard normal curve, you could do that. Yeah, so 1.71. So our standard normal curve is very good for all different kind of distribution, uniform for the normal distribution or central limit theorem. It works perfectly. Okay, so probability for sample mean less than 64 is same thing as saying for z-score less than 1.71. So now go to table A2, look for the corresponding probability. Okay, 1.71, and that should be 0.9564. Okay, 0.9564. So 0.9564. And that's what we're looking for. One more time, let me double check. Yep, that's good. .9564. For PAPI. Okay, and this is question 10. Let's go back to question 11. Okay, so you're given this confidence interval, right? And in this form, you want to find out what is p hat, what is margin error. Okay, actually it comes from this solving a system of linear equation. And let me show you one time, and you should be able to get it pretty quickly. No, not this one. Need to print the other screen. Okay, print screen. paste it. Make sure I share the right screen. Here you go. So we are given this one, and we know that this is a lower limit, meaning it's p hat minus margin error, and this is upper limit p hat plus margin error. So basically what you're looking at is p hat minus margin error equal to 0.111, and p hat plus margin error equal to 0.777. So this is what we call a system of linear equation. Remember back in the algebra course, if you have x minus y equal to 0.111, right? And then x plus y equal to 0.777, right? Exact same concept, just different variables. Now, if you want to find out the p hat, just adding the two equations. Okay. If you add both equations, you're going to get twice of p hat, right? Margin error cancel each other. So you get 0.11 plus 0.777, it's 0.888. And in order to get a p hat, you divide 2 from both sides of the equation, you get p hat. So p hat sample proportion equal to 0.444. So now you find that. And second thing is find the margin error, right? So easiest thing to do is plot this into the second equation. So you get 0.444. Adding margin error equal to 0.777. And this is a linear equation with one variable. So subtracting 0.444 from both sides of the equation, that will do it. Cancel the number, margin error equal to 0.333. Okay, so you find both. So basically just using some algebra, right? You'll be able to get this fairly quickly. So 0.444, that's one, and 0.333. Okay. Any question on this? Very good. Okay, so now question 12. All right, it's about the coefficient, linear correlation coefficient, right? Linear correlation coefficient. And what value of the coefficient of determination? Coefficient of determination is the square of, it's basically r squared. So you just square r, right? So what it's saying is squared r. So basically it's a negative 0.8 squared. And it becomes 0.64. So the r square is always positive, right? Because it's square. Okay. So now we get that 0.64. So what percentage of the total variation that could be explained by the linear relationship between the two variables? We turn this into percentage, it would be 64%. So this is exactly the notion of the coefficient of determination. And basically show you how good your model is, right? How good is the regression model or regression equation? Here is a 64% effectiveness in terms of predicting the dependent variable y. Okay. So that's question 12. Question 13. So very similar one, right? They're given this confidence interval, and the lower limit is p hat. I can do it one more time. No problem. Again, we are given this confidence interval, and we want to find out both numbers. Similarly, we are given the lower limit. Okay, so p hat minus margin error, that's 0.503. P hat adding margin error, upper limit is 0.593. So now in order to find the p hat, again, it's a system linear equation, adding both equations. Okay, so you get margin error get canceled, you get twice of p hat equal to 1.096. Okay, now next step, you're dividing both side equation by 2. So p hat equal to 0.548. Once you find out p hat, now we apply into the second equation. So it's 0.548 plus margin error, 0.593. Now again, one more time, subtracting both sides of the equation by 0.548. So the difference is the margin error. So margin error equal to negative, no positive. It has to be both positive, right? Due to the using the formula, both results must be positive. 0.045. We good? And you can just put both numbers here, right? 0.548 and then 0.045. Okay, let's do it. Okay, so this is question 13. Let's look at question 14. And this one, we are given a couple things, right? Sample size, number of successes in the sample, and also confidence level. So you want to find out margin error. So we need to use the formula. So again, we go to the, first of all, we find out what is the p hat, the sample proportion, meaning the sample success rate. All right, so now let's go to the note. X represent number of successes in a given sample. Then the sample size is 550. So we can find out the sample success rate, which is what we call a p hat. P hat is always equal to number of successes X over sample size. So it's 110 over 550. And this turned out to be 0.2. The Q hat is the complement. So if you know P hat, you know Q hat. Q hat is a failure rate, right? Percentage of failures in this sample. So it's 1 minus P hat, it's 0.8. Okay. And now once you know both and the confidence level, that gives us critical z-score, Z alpha over 2. And that should be 1.645. How do we get 1.645 so quickly? You go to table A2.
You don't see your screen.
Okay, I probably forgot to share. Here you go. Can you see the screen now?
Yes.
Okay, so p hat first, x over n, right? That's how you calculate the p hat. Number of successes over the sample size. And then q hat is the complement of p hat. They are complement of each other, so 0.8. And based on 90% confidence, if you go to the table A2, here you go. And go to the second page of table A2, you see confidence level, 90%, critical value, critical z-score is 1.645. Okay, so we get that 1.645. That's how we get this. Now, next thing is find out the right formula, right? To find the margin error. So one more time, you go to the formula sheet. And this is from chapter 7. And this is exactly the formula we're looking for, right? Margin error equal critical z-score times square root of p hat q hat over sample size. Yeah, that should do it. So now let's go back. So margin error equal to critical z-score, z alpha over 2 times square root of p hat times q hat over sample size. Okay, and throwing out the numbers, 1.645 times square root of 0.2 times 0.8 over sample size is 550. Okay, so 550, this is sample size. Yeah. So now let's find the margin error. They want 4 decimal places. Again, I'm going to show you in Excel. One more time, put in the 1.645 times square root. Okay, 0.2 times 0.8, dividing by 550, close it. And You got it. So here you go. And we want 4 decimal places. Okay, 0.0281. 0.0281. And 0.0281. Okay, that's what we're looking for. Okay, and the margin error. And basically for chapter 7 and 8, typically you have a standard procedure and then just calculate each element from the formula, step by step. You'll be able to get to the final solution. Okay, that's question 14, 15. All right, so they very similar one. Now they want to construct the confidence interval, right, with the 90% confidence. The number varies a little bit, but the procedure is very similar. So it's like one step away, right? Before we can get to the confidence interval, we need to get a margin error. So let's look at it. Okay, so now here, let's find the p-hat first, just like the other one. P-hat equal x over n, 360 over 600. This turned out to 0.6. And then the q-hat is a complement. Q-hat equals 1 minus p-hat. So 1 minus 0.6, that's 0.4. And then since it's 90% confidence, just like the other one, critical z-score, it's 1.645. Now, sample size, we know that 600. I'll find the margin error first. Critical z-score times square root of p-hat times q-hat over sample size. Now I'm plugging out the numbers, 1.645 times square root of 0.6, right? 0.6 times 0.4 and over 600. And let's do it. And then we want to run to 3 decimal place because the answer wanted 3 decimal places. Now let's go to Excel. Let's calculate the result. 1.645 by square root 0.6 times 0.4 divided by 600 and close it. All right. And let's see what the result is. Okay, 0.0329. If you want to run it to 3 decimal place, that's fine. So it's 0.033. Okay. So now we get 0.033. 0.033. Okay. And now, so this confidence level, confidence interval, we try to construct. We know p-hat, basically p-hat subtract margin error, that's lower limit. And p-hat adding margin error, that's upper limit. And we know p-hat is 0.6. So we're using 0.6 minus margin error give us lower limit, 0.6. And 0.6 plus margin error, so 0.6 minus 0.033. And the upper limit is 0.6 adding 0.033. So this interval contains true population proportion. So this is 0.567 lower limit. Upper limit is 0.633. Okay, and we get that. And you just throw in both numbers into this interval, then we have it. Okay. And that's pretty much how you construct a confidence interval. And always start with the margin error. Now, once you have margin error, then we have the confidence interval. Okay, this is question 15. Okay, question 16. And it's about finding the sample size. And here the special thing is p hat, q hat unknown. So when p hat, q hat unknown, you can assume both becomes 0.5. And using 0.5, we will guarantee, we are being conservative, meaning the sample size will be large enough to accommodate this requirement. All right, so one more time, print the screen. And then the formula we are using here is this one. Sample size, when the p hat, q hat unknown is this, right? When they are unknown, we are using this. So both using p hat, q hat equal 0.5, p hat times q hat becomes 0.25. Okay, that's how they put this 0.25 here. All right, so let's go to the note, work it out step by step. So one more time, margin error is given. So we know this thing, margin error. So E equal to 0.03. So 90% confidence level. Indicate critical z-score. It's 1.645, right? And p hat, q hat unknown. So both p hat equal to q hat equal to 0.5. Okay, now sample size should be critical z-score square times 0.25 over margin error square. Okay, so now let's throw in our numbers. 1.645 square times 0.25 over 0.03 square. Okay, and we're going to get a decimal, and the running rules here is always run up to the next whole number. So let's put it in. Okay. Also, it's 1.645 square, critical z-score square times 0.25, and dividing by, if you want to put denominator in parentheses, that's fine. If you want to put numerator in the parentheses, that's okay. Okay. And then the denominator will be 0.03 square. And let's do it. And just hit enter, right? You get that 751.6736. It has actually many more decimal, right? If you want to, so that's what it is. But we always run up 751, 67, 36111. And we run up the next whole number, no matter what decimal we're looking at, right? Always run up. We want to be conservative. So picking up a bigger sample size, usually it's much better, right? You guarantee a better result. Okay, so 752 is the answer. So this is question 16. Question 17. And very similar one, right? But here the p hat is given. P hat is 36%. Okay, so we're using this formula. P hat, q hat given. With this. All right, let's go back here, print screen. Now list all the information we have here. Okay, let's list it. So margin error, 7 percentage point. So margin error equals 7%. So that's 0.07. Okay. Confidence level is 95%. So the critical z-score is 1.96. Okay, and then p hat is given, right? P hat here is 36%. So 36. You know p hat, you know q hat is 1 minus p hat. So 1 minus 0.36 is 0.64. How do we get 1.96 for critical z-score? One more time, let me show you. This is from the table A2, second page of table A2. Right here, 95%. it's a shortcut. If you want to get that right away, just recap on bottom. Or you can draw the bell curve and then get it from the bell curve as well. 1.96. Okay, so we have all the numbers we need. Now we want to find our sample size. Here we go. So it's going to be critical z-score square p hat times q hat over margin error square. What we have to do is throw in our numbers 1.96 square times 0.36 times 0.64 dividing by 0.07 square. So now one more time, we want to put into the Excel, get the result. Okay, here we go. 1.96 square times 0.36 times 0.64. That's numerator divided by denominator, 0.07 square. Now we'll do it. Okay. And if you enter, that's give us a result. 180.6336. And again, due to the rounding rule, we will run up to next whole number. 6336. Infinitely many decimal places run up to 181. Okay, so the smallest sample size, minimum sample size required will be 181. Of course, you can, in the reality, in the real life, if you can get a better, bigger sample size, it's going to be better off. That will minimize the margin error, right? Even further. So that's just from a practical point of view. Okay, now let's look at question 18. So we're halfway through. Okay, so what is a single value used to approximate the population perimeter? We call that sample statistics, right? The point estimate, yeah. Point estimate is a single value called a sample statistics used to approximate the population perimeter. And this is what we call a point estimate. And there's another method called confidence interval, right? We just did some calculation on that to get a confidence interval. Now, which the following will be the correct interpretation of a 99% confidence interval, such that population mean mu is greater than 0.4.1, less than 5.6. So 99% confidence indicates we are 99% confidence, right? Or 99% confident that interval from 4.1 to 5.6 actually does contain the true value of the population mean mu. Okay, that's exactly the interpretation of this confidence interval, right? So it would be. Okay, that's question 19. Question 20. Which of the following is not an equivalent expression for this? Okay, so basically they want you to find out this sample mean and also the margin error. So then let's do a calculation really quickly. So that will make it a lot easier to look at the result and pick the right choice. All right, one more time. We just have to find out the sample mean, also the margin error. And this is the confidence interval for population mean mu. So the lower limit is sample mean minus margin error. Upper limit is sample mean adding margin error. So again, we're going to have a system of linear equations. X bar plus margin error, upper limit 89.5. Sample mean minus margin error is 161.7. And if you add into equations, we'll be able to find out the sample mean right away. So we get twice of the sample mean, margin error get canceled, adding 189.5 plus 161.7. Let's see what that is. Excuse me. Adding 161.7 So 351 twice of sample mean equal to 351.2. So now we divide 2 from both sides of the equation. That will give us sample mean equal to 175.6. That should be right. 175.6. Okay. Now we know the sample mean, and we can just plot here to get a margin error. So 175.6 adding margin error equal to 189.5. And from there, we'll be able to find out the margin error. So subtracting 175.6, difference is margin error. So margin error equal to 189.5 minus 175.6, 13.9. Okay. So 175.6 plus minus 13.9. This is good. And this is good. Also, this one is good. So the only thing is not right is C, right? C is not a correct answer. The sample mean must be 175.6. And by finding both, it will be very easy to make a determination on the correct answer. Okay, and let's see, 21. All right, so they want you to find a critical z-score here. Now the confidence level is not one of those 3 special ones. So we have 90%, 99%, 95%. Those 3 are special ones. And when alpha equal to 0.07, what it's saying is we need a 93% confidence level, right? That's what it is. So based on that, we'll be able to find our critical z-score. Let me show you how to do that one more time. Again, you draw a bell curve. And we know it's two-tailed test, so this matters a lot. And this is for the hypothesis testing, right? Two-tailed test. First of all, bell curve, draw it. And the critical z-score located on both tails, right? So we have -1 right here. And a +1. And then on two tail, the total probability is 0.07. That means on each tail will be 0.07 by 2. So that's going to be 0.035. This is 0.035. So now we're going to use this area to the left, find out -1 first, which is very easy to do. So using probability of 0.035, go back to table A2, find out the critical z-score here, the -1, and then the +1 will be the opposite. So now one more time, let's go to table A2. 0.035 on the first page of table A2. And let's see what the closest value is. Here we go. This is the closest value, 0.0351. Ours is 0.035, and this is the closest you can get. So it's -1.81. So the critical z-score here is -1.81. Go back and then -1.81. That's -1. +1 is exactly the opposite. It's 1.81. So the answer should be 1.81. They always want +1, right? And you want to run it to two decimal places. And that's the easiest thing to do using the symmetrical property. Get -1 first. It's easier to find. And then find a +1 accordingly. And that's 21. Okay, let's look at question 22. Okay, right tail test, alpha equal 0.02. So this is another example. It's only one tail now. Right tail, and we know area on the right tail is 0.02. Okay, let's see. So draw the bell curve, and then we're looking at the right tail. And the right tail is area is 0.02. That means on the left tail, the total area is 0.98. Okay, 0.98. 0. Now you're gonna go to the table, look for the closest match. Remember, we always use area to the left. We cannot use area to the right as a reference number from the table. 0.9800 should be on the second page. 9800. This is closest value, 0.9798. The other one is also kind of close, but not exactly the closest one, right? 0.9803, 0.9798 actually is closest one. So we're going to take that value. And the corresponding z-score is 2.05, 2.05. Okay, and that's what we're looking for, 2.05. Okay, and this is what we call 98% confidence. Because alpha equal to 0.02. The confidence level is always the complement of alpha. Okay, that's question 22, 23. Okay, using the final value of the z-score, test statistics using this. Okay, so we get a, using this formula, find out the test statistics z-score. Claim that the proportion of p's with yellow parts is equal to 0.25 or 25%. So p hat is given, right? Because no, actually this is p. It's about the entire, the claim is always about the entire population. So we are given p equal to 0.25. Okay. Let me share the screen now. In the note, and let's work it out step by step. So this claim always is about the population proportion p, right? So p is given, p equal to 0.25. And the sample statistics from one experiment, this sample statistics with 430 p's, n equal to 430. 90 of them have yellow parts. That means p hat equal to x over n. So that's going to be 90 yellow parts over 430. Okay. And let's see what that is. Typically, we run it to the more decimal place will help. So let's see, 90 by 430. This turned out to be 0.2093. So I'm going to keep as 4 decimal places. And if you know p hat, you know q hat. Q hat is 1 minus p hat. So it's 1 minus 0.2093. So this is 0.7907. So the p hat, q hat sample size, we know p as well. Now we can calculate the test statistics z-score. So z-score equal to p hat minus p over square root of p times q over sample size. So since we know p, we know q, right? Q is 1 minus p, 1 minus 0.25, it's 0.75. Now we throw in numbers into the formula. P hat is 0.2093 minus 0.25, dividing by square root of 0.25 times 0.75, dividing by sample size, which is 430. And let's find the z-score. They wanted 2 decimal places. .2093 minus 0.25, dividing by open parentheses, and we get square root 0.25 times 0.75, dividing by 430. And let's do it. Okay, so now you enter, you get a result. And 2 decimal we want negative 1.95. That should be the proper answer. Negative 1.95. That's question 23. And question 24, given the use of given information behind the p-values, so you we need to do p-value. So test statistics in the two-tailed test is z equal to 1.94. So that we want to find out p-values. Okay. Basically, you want to find out probability on both tails, right? It's a two-tailed test. That being said, because it's a two-tailed test, so the one on the right tail is 0.94, and the other one on the left tail, z-score will be negative 1.94. So the easy thing to do is use the one on the left tail, find out area on the left, and area on the right is the same, right? Because it's symmetrical with respect to center. So let's find this one first. Corresponds to the z-score of negative 1.94. Negative 1.94. See what that is? It turned out to be negative 1.94. It's 0.0262. 0.0262. Okay, so we find out the area on the left tail. So this is 0.0262. Because it's symmetrical, so on the area on the right tail is also 0.0262. If you sum up those, that's a p-value we're talking about. And this is what they call the p-value method. So adding 0.0262 or double that because it's two tail. So it's 0.0524. And you look at this probability. So this probability is 5.24%. So if alpha equal to 0.05, meaning it's slightly bigger than alpha, so it's okay, right? Meaning we fail to reject HO. Okay. If this, let's say we want 99% confidence, meaning alpha equal 0.01, then we reject HO because this probability is much bigger. Okay. So the p-value is basically using this probability to determine whether or not this is a valid claim. This chance for this claim to occur is 5.24%. So this is question 24. Question 25. What is the procedure for testing a claim about property of the population? We call this hypothesis test. Hypothesis test. Okay, that's 25. 26. And this one, the test statistics value used in making decision about null hypothesis, and it's found by converting the sample statistics to a score. right? We call this test statistics Z-score usually, with the assumption that null hypothesis is true. Okay, so test statistics is what we are using. And we just did a calculation on one of the test statistics for to test the claim about population proportion P. All right, the 27 test the following claim, and this is from chapter 8. So all these questions are in the sequential orders. We start with chapter 6, 7, now 8. Then we get to chapter 10. Test the following claim, identify null alternative hypothesis, test statistic critical values, conclusion about null hypothesis, and the final conclusion addresses the original claim. So we have a simple random sample 50 salaries. So we get a simple random sample here. Professional football coaches average salary of $104,533. The standard deviation of all salaries of professional football coaches, $462,612. And this is standard deviation, right? And this is population standard deviation because it says all. So we know it's a population standard deviation. Since population standard deviation is given using z-test, is the population standard deviation is not given using t-test. So use alpha, which is 0.05, alpha equal 0.05, indicating we want 95% confidence. To test a claim that's mean salary of professional football coaches less than 500,000. This is less than, there's no equal sign. So this has to be an alternative hypothesis. So the mu less than 500,000, that's alternative hypothesis. Okay, and then only two options match that, right? B and C. Only B has an equal sign here, so it has to be B. Okay, remember, null hypothesis must have equal sign, right? So this is a valid claim. The null hypothesis is mu average salary for entire population equal to 500,000. Alternative hypothesis mean less than 500,000. Okay, now we want to calculate the test statistics. Okay. All right, so I'm going to show you details in a bit. Okay, here we go. And the formula we are using here, let's go to chapter 8, formula sheet. Here we go. So the sigma is known. So we're using this formula, right? It's like the same formula as the central limit theorem. And to be sample mean minus population mean divided by population standard deviation over square root of sample size. Then that's how we calculate the z-score. Now here, sample mean minus population mean divided by population standard deviation over square root of sample size. Sample mean this, right? 404,133. Population mean this, 500,000. And population standard deviation is this, 462, 612, and dividing by square root of sample size, which is 50. And let's see what that is, right? Put into the Excel. $404. 433. 414,533 minus 500,000 and dividing by square root 462, 612. And that should do it, right? So here you go. So we get a negative 1.31. Negative 1.31. Okay. That's the value of the test statistics. Okay. And then let's identify the critical value of the z-score and then whether to reject it. So based on this is one tail, and we call this its left tail. So because mu is less than 500,000, so let's draw the bell curve. Identify this critical z-score. Okay, so on the left tail, we have total area, alpha is 0.05. So it's right here. This is 0.05. And that will give us the critical z-score here. Okay, and based on that, let's see what the critical z-score is. And this is what we call the rejection region. Using the rejection region method. Left tail is a rejection region, and everything to the right is non-rejection region. Then let's see. Now go to table A2. .05. And if you look at the corresponding z-score is negative 1.645, right? It's right in the middle of 0.0505 and then 0.0495. And this corresponding z-score is negative 1.645. Negative 1.645. Okay, and this number is actually bigger than that. Okay, this number is bigger than this. So this number falls in the non-rejection region. So meaning we fail to reject HO. Because this number falls in the non-rejection region. So that would take care of the rest of this, right? The value of the critical z-score is negative 1.645 and fail to reject HO. So fail to reject HO. So that's not sufficient evidence. Let's see, less than that, right? So that's not. You see, they want you to comment about the alternative hypothesis. So there's no sufficient evidence to support a claim that the average salary of, because we fail to reject HO, meaning we are accepting HO, so we are rejecting H1. So that means that we don't have enough evidence to support a claim that the average salary of football coach is less than 500,000. Okay, and that will be the complete process of the hypothesis testing. We are testing population mean mu here. Okay, and this is question 28. Okay, and starting from this question, the rest of them is all about chapter 10, correlation and regression. So you just gotta plot a linear correlation coefficient R to determine whether there's a correlation between the two variables using alpha equal 0.05. And so here we need to do a data entry first and input this into the Excel. Okay, so open Excel, do a quick data entry really quickly. 4, 1, 4, 3, 2. And second one is 7, 4. You can also do a quick data entry really quickly. 4, 2, 1, 3. Okay. Here we go. So we get this data set here, input it properly, then quickly double check the number. 41432 74213. Okay, that's good. How about this? Okay. Now we need three things, right? X times y, x squared, y squared. So x times y, it will be this times the x squared, square the x. And get all the square numbers. Okay, then square all the y. C2 square, get that. Now we're gonna get all these numbers. Okay, now we need to calculate the total. Which column? Sum of x, sum of y, sum of xy, sum of y x square, sum of y square. Okay. And we need to calculate B0, B1 also, right? Let's see, what do they want us to calculate? So quickly look it up. Given the scatter, does that suggest as a linear correlation, meaning we need to calculate the R, right? That's the only thing we need. Okay. Let's use the formula to calculate the R. And if you go back here in the formula sheet, on the chapter 10 formulas in the formula sheet. And this is the formula we are using to calculate the correlation coefficient R. And let's get the numbers really quickly. So R to n times summation of x, y. So sample size here is 1, 2, 3, 4, 5, right? So it's 5 numbers here. So that means sample size is 5 times summation of x, y, that's 49. Okay. I'm using exact number so you will not feel confused. And minus summation x is 14 times summation of y is 17. Okay, now take out the numerator, and then now we have a square root n sample size 5 times summation x squared is 46 minus summation x 14 squared. Okay, and multiply by square root. Sample size times summation of y squared 79 minus summation y 17 squared. And let's do it, right? So that we get 0.1166. Should be 1. Let's quickly double check that. Even better, right? If we can double check using this formula called COREL. So this is the formula you can double check whether you have the right calculation or not. Right? Just input the x values, input the y values, and you get the same thing, right? And then get a confirmation by using the formula, also this shortcut. Okay, so it's 0.1166. They want 4 decimal places. Okay, so we get that. Let's go back. So this correlation coefficient is quite low, right? Compared to the other ones, you know, this is fairly low. So this is a scatter plot. Straight line pattern. Yeah, so given the scatter suggests there's linear correlation. I don't think so, right? Because it's very, very vague linear correlation. So because the point does not appear to have a straight line pattern. Yeah. Okay. Yeah, does the correlation coefficient indicate there's a linear correlation between the two variables? It's a linear correlation, but it's a very weak one, right? So no, because absolute value. So now we're going to compare this correlation coefficient with the critical values. So the critical value alpha equal 0.05. So now let's look at it. So in this one, sample size is 5 and alpha equal 0.05. So this critical value is 0.878. So meaning this correlation coefficient has to be bigger than this in order to validate this linear correlation between those two variables. So in this case, there's no linear correlation between these two because our correlation coefficient is much smaller than the critical values. The critical value is 0.878. Sample size 5, alpha equal 0.05. Okay. Yeah, so that also validates the conclusion from the previous one. No. Because absolute it's less than the critical value. Yeah, so it should be A. Yeah, so that will do it. Okay. That's 28, 29. We are given this R equal 0.415. So the coefficient of determination will be R squared. If you square the R, you get 0.415 squared. And it's 0.172, right? If you run into 3 decimal place, so the coefficient of determination is 0.172 once you square this number. So that means 17.2% of the variation is explained by the linear correlation, 82.8%. So remaining percentage is explained by other factors, right? Besides this one, besides the one presented in the question. So 17.2% is not that effective, right? You only explain 17.2% of variation. It's not very good. Question 30, when determining that whether there's a correlation between the two variables, one should use a data visually. Yes, scatter plot, right? We always do come up with the scatter plot first, and then explore data whether there's a correlation between those two variables. Now, which of the following statement about correlation is true? I think it's B. We say that there's a negative correlation between X and Y if the X value increases and as the corresponding Y value, no, this is positive, right? So B is not right. Let's see, positive. They should move in both same direction. I think it's positive correlation. Yes. Okay, D should be right. We say there's a positive correlation between X and Y if the X values increases as the corresponding Y values increases. So when they move in the same direction, it's positive correlation. When they move in the opposite direction, then that's negative correlation. So D is the right statement. Everything else is wrong. Okay, 31. 32. All right, so now we have this. The linear correlation coefficient R is 0.943. You are given a regression equation. And the thing is, we got to make sure, you know, this is good number for this case. So we're going to quickly check this correlation coefficient first compared to the critical values. So the critical value for sample size 20 and alpha equal 0.05.
What if it wasn't a good number?
I'm sorry, one more time.
What if it wasn't a good number?
And then we have to use the average. You see, that's why they provide the average here. So the average of 20x, all the 20x values and then 20y values, if this number is not good, meaning it's not bigger than the critical values, then the best predicted IQ score of older child will be this number, 99.75. If this correlation coefficient is good, then we're gonna get a best predicted IQ from the regression model here. Okay, so that's the difference. That's why they present both. They give you both piece of information, and you have to decide which one is the right way to go. Okay, now one more time. Sample size 20 of 0.05. We get the critical value. It's only 0.444. So the linear correlation coefficient R is much bigger than the critical values. So that means this regression model is it's a very good one, right? And the bigger it is compared to the critical value, the better it is. The better the model is. So now we're going to use this regression model to make a prediction about the IQ score for this older child. So X value here is 90. So replace X with 90. So 90 times 1 adding and subtracting 1.32. That should give us the best predicted IQ score. So the 90 negative 1.32 plus 1 times 90. So it's 88.68, right, for this question. And we're not using this one because this regression model is good enough. So we utilize the regression model to make the prediction about this IQ score. Okay. Yeah, so 88.68. So question 32. Now question 33. Now we need to find out the B0, B1. Okay. So I'm going to export it into the Excel, and then we're going to come up with B0, B1 from there. Let me share the screen with you guys first. Okay, here we go. So this data set we are working with. Okay. And we need 3 more columns. XY, X square, Y square. Let's find the product of XY first. This times this. And find the square, X square. Y square. All of that. And then you just sum up all the X values, sum up all the Y values, sum of XY, sum of X square, sum of Y square. Now let's calculate the B0, B1 first. So B0. Okay, B0. Is the total of Y. Okay, total of Y is 10 times total of X square, which is 24, minus total of X, which is 10 times total of xy, which is 28, and dividing by sample size, in this case is 5 times total of x squared 24 minus total of x 10 squared. And we get b0 is -2, and then b1, let's find the b1. Again, using the formula. And b1 is times the sample size 5 times total of xy, which is 28. Okay, and minus summation of x, total of x, 10 times total of y, it's also 10. That's numerator and divide by denominator, sample size 5 times total of x squared, which is 24, minus total of x, 10 squared. That's on one of these -2, one of them is +2, I think. Yeah, that's good. Okay. All right, so that we get both. That's what it is. Okay, that's 33, 34. Okay, and this one I'm gonna do it really a little bit quickly, right? So okay, so let's get the copy to Excel really quickly. Share the screen with you. So let's find a total. And you can just change the first column to X, change the second column to Y. Right? That's what it is. In reality, that's when we're using the formula, that's what we go by. Orders and order. Okay. And again, we're going to calculate x, y, x squared, and y squared. Same procedure. So x times y. That got each one of them. Get an x squared. That. Never got that. And then square the y. Just like we did in your project and your homework assignment, and we sum up each one of them. Total, total, auto sum, total, total, yeah. So now we have all numbers, and similarly B0 and B1. Okay, B0 first. So sample size, again, it's 5 numbers here, 5 times total of y, 773 minus summation next, which is 455 times total of xy, 71058. Now take a numerator and divide by sample size 5 times total of x squared is 42087 minus summation x, 455 squared. And we get B0. Okay. So it's fairly large number. Okay, let's see. Summation x, summation times summation xy. Yeah, it's good. Okay, so that's what it is. Big number, B0. Okay. Look slightly off, but let me quickly check. Total of this, total of this. That's y, that's good. It's all good. Okay. Nothing wrong. Square. Yep, it's all good. So yeah, that's going to be sample size 5 times summation of y, it's 773. Oh, yeah, no, there's no sample size here. Just summation of y times summation of x squared, which is 42087. I overlooked the formula. So summation y is 773 times summation x squared, which is 42087, times summation x 455 times summation xy. That denominator is good. Okay, so it's 59.196. I think they want 2 decimal. And B1. So B1 is sample size 5 multiplied by summation xy 71058 minus summation x 455 times summation y 773. So that's numerator divided by denominator, sample size 5 times total of x squared 42,087 minus summation x, which is 455 squared. Okay, that'll do it. And this turned out to be 1.05. Run into 2 decimal place. That would take care of the first part. And the second part is 50. Yes, given that the systolic blood pressure is 85 milligram. Will be the, so we still get a double check, make sure there's a correlation here. So that's quickly calculate the correlation. I'm gonna use a shortcut formula, right? So using COREL, you can use it, definitely use the formula from the table, you get the same result. We are running out of time, so I'm gonna do a quick shortcut. Okay. So this is 0.6266, that's the correlation coefficient. If we go back, let's check the table, make sure it's bigger than the critical score, right? So sample size is 5, alpha is 0.05. So I think it's much bigger than that. 5, alpha is 0.05, 0.878. Our number is 0.826. No, so it's not bigger than that. That means we cannot use the regression model. The regression model is not good enough because due to the fact that we rejected, there's no correlation because R is smaller than Alpha value. So reject HO. It's less than, yeah. So we fail to reject HO. So there's no correlation. That means we cannot use the model to make a prediction about the population parameter. So this best predicts systolic blood pressure will be in the right arm, okay, left arm. So you just add up those numbers. We did it already. So the best predicted value it's gonna be this by 5. So it will be 154.6. Okay. Because the model fails, right? The R is smaller than the critical value R. So model fails. So we got to average those Y value to get the best predicted value in this case. Okay. So it will be 154.6 without using the model, right? Model is not good. Okay, that's question 34, 35. In the scatter plot outlier, right? It's a point lying far away from the other data points. Right? We call this outlier. Okay. Okay, that's 35 and 36. Yeah, so you are having this regression model. So the Courtini level, it depends on the tau, right? So this is regression model based on 29 sample, 29 cigarettes, find the relationship between the amount of tar and the nicotine in cigarettes. Could be modeled by this regression equation below. If a cigarette has 12 milligram tar, okay, what is the single value that best predicted amount of nicotine? Assuming there's a linear correlation between this. So we just basically replace tar here with 12. So we basically do 0.159, adding 0.0 656 multiplied by 12. And that turned out to be 0.9462. And this is best predicted, 9462. Okay. And this is best predicted amount of the nicotine in this cigarette. Okay. And that completes the final exam review. And something I want to mention really quickly. So, pretty quickly, right? When you finish the final exam on Wednesday, I will transfer all the grade in a math Excel to the Blackboard. So in the Blackboard, under the grade center, you will see a weighted grade. And then also I will follow the grade distribution from the syllabus. Okay, like in the syllabus, each one has different weights. I will multiply the grade, each proper grade by the weight, and then come up with the final course grade under the Blackboard. And this is how it will be calculated, right? Excel project outside the weight for each project, and then homework 15%, quiz is 20%. I put in 1 grade for homework, 1 grade for quiz, the best possible grade for midterm, final as well. And you get a final course grade calculated under the Blackboard. So eventually, after Wednesday, hopefully by Thursday or Friday, I'll be able to finish grading process. I will submit a grade by then. Okay, so that's why I can't give you any more extension on the homework and quizzes. So Wednesday will be the last day to complete all of them. Okay, and or if you need to make up something, let me know. Right, Wednesday is last day. Okay, do you have any question before we end the section? So this Wednesday, you're taking the final, right? So you have to log into the Zoom session. This Wednesday is one time. You log in Zoom session, taking the final, submit a final exam. And that will be it, right? And after Wednesday, no more class meetings, right? So Wednesday, I've talked to you guys at 9:10 a.m. Okay, same time, right? 9:10 until 11 a.m. you're taking the final exam on Wednesday. Okay, any questions before we end it? Okay, guess no questions. Again, I'll see you guys on Wednesday, right? Okay, bye-bye, guys.
Thank you, Professor.
No problem.
You.
You.
Thank you.
No problem. Okay,
Professor,
no problem. Bye-bye, guys.
Professor,
Yes, yep.
are you saying you'll see us on Wednesday? Are we logging on for the midterm on Wednesday, or do we just take it on our own?
No, it's same thing. You join the Zoom session and you take it during the Zoom meeting session.
Oh, okay. All right.
So join the Zoom meeting, right? Using the same link.
Yep. Okay. Thank
All
you.
right, no problem.
Sorry.
We'll see you Wednesday. Bye.